What if the universe isn't just, a collection of inert particles and predictable forces, but something more?
Hmm.
Alive, like a breathing, self-organizing system that's constantly actualizing its own potential.
Yeah, it's a pretty profound thought, isn't it?
It really is. And for decades, physicists have been on this grand, almost mythical quest for a unified theory, that elusive theory everything, something that can explain, well, everything we see,
Yeah.
from the tiniest subatomic particles doing their quantum dance.
All the way up to the vast, swirling galaxies stretching across the cosmos. Yeah.
Exactly. And in this huge quest, string theory has really been the dominant player for a long time. It's mathematically beautiful, this idea of vibrating strings. And then you have the concept of brains, these multidimensional membranes, sort of the surfaces our universe might live on.
That's the picture, yes. Elegant, certainly.
But what if, in the shadows of this established giant, there's a bold new paradigm emerging? Kind of profound intellectual response to string theory's own limitations, something proposing entirely different things like dynamic hyperfractal layers and a universe driven by coherence.
A fundamentally different approach, yeah.
So today, we're going to take a deep dive into this fascinating and frankly pretty mind-bending world of theoretical physics. We'll be specifically comparing these two groundbreaking ideas that aim to explain everything. The established string theory, which, let's face it, has captured imaginations for ages.
Absolutely. Yeah.
And this provocative new hyperfractal, hypersymmetry, hypergravity coherence resonance theory of everything, or let's just call it the HHHCR2, for sanity's sake.
Good plan.
Our mission today is to really unpack their core ideas, explore their profound, almost philosophical differences, and, discover what each might truly mean for our understanding of reality itself, and maybe even consciousness.
It touches on all of that, definitely.
So get ready for some serious aha moments, because we're about to explore concepts that genuinely redefine what we think we know about existence.
Buckle.
Okay, so let's unpack this grand quest for a unified theory. For decades, physics has been wrestling with fitting these notoriously stubborn pieces of the cosmic puzzle together. You've got gravity on the large scale, Einstein's general relativity.
Right, governing planets, stars, galaxies.
And then the microscopic, probabilistic world of quantum mechanics. Plus the Standard Model, which does a great job with electromagnetism, the strong and weak nuclear forces, and all the fundamental particles we found.
It's incredibly successful, the Standard Model.
But the challenge has always been that general relativity and quantum mechanics just don't play nicely together. They work brilliantly in their own domains, but fundamentally contradict each other when you try to combine them.
The incompatibility problem, yes. It's the central challenge.
So for so long, what's been the main contender trying to bridge that divide? What's its core idea?
Well, you've put it perfectly. For a significant period, string theory has really been at the absolute forefront of this ambitious search for unification.
Right.
Its core idea is, I think, quite elegant in its simplicity, but really profound in its implications. It proposes that all matter, all force interactions, they don't come from what we traditionally thought of as point-like particles, tiny featureless dots.
Like a little billiard ball.
Exactly. Instead, it suggests that these fundamental bits of reality are actually tiny, one-dimensional, vibrating strands of energy, strings. I imagine them like infinitesimally thin rubber bands, way too small to ever see directly.
Yep.
And the different ways these strings vibrate, their unique vibrational modes, that's what determines what kind of particle or force they represent. So an electron is just a string vibrating in one way, a photon in another, a quark in yet another. It unifies matter and force through vibration.
So everything's just different notes played on these fundamental strings.
That's a great analogy, yeah. Different vibrations, different particles. Now, within this framework, string theory also introduces something equally crucial: brains.
Right. You mentioned those. Short for membranes.
Exactly. And they're conceptualized as multidimensional surfaces, often imagined as being embedded within a higher dimensional space, sometimes called the bulk.
Okay, so higher dimensions.
Yes. Think of it like this. If a string is a 1D line, a brain is a higher dimensional surface. Could be 2D, 3D, even higher. You can visualize them as these cosmic sheets or vast surfaces where the strings can attach or end or maybe even propagate along.
And our universe could be on one.
That's one of the key ideas. Our whole four-dimensional universe 3 space, one time, might actually be embedded on one of these brains, like a flat image existing on a much larger, possibly curved higher dimensional surface.
Okay.
And a key point about these brains, at least in most standard formulations of string theory, is that they're generally considered static surfaces. They provide a fixed, unchanging backdrop for the strings, which are the dynamic things vibrating away. The brains themselves don't really evolve or change. They're the stage, not the actors.
So they just sit there.
Pretty much. Now, to make string theory actually work with the reality we see, which appears to have only 4 large dimensions, it needs this concept of hidden dimensions, what physicists call compactification.
Compactification. Right. Heard that term.
It basically means that the extra dimensions the theory requires, usually 6 or 7 more, making 10 or 11 total, are curled up, compactified, into unobservably small, intricate shapes.
Like how small?
Incredibly small. Think of a garden hose again. From far away, it looks like a one-dimensional line, but get close, and you see it has a second, small, curled-up dimension, its circumference.
Okay, I can picture that.
String theory says the extra dimensions are curled up much more complexly than that into things like Calabi-Yau manifolds. These are incredibly intricate mathematical shapes, and the extra dimensions are supposedly contained within these tiny, curled-up spaces, making them impossible for us to detect directly with current tech.
So they're there,
Yeah.
just hidden because they're tiny and folded up.
That's the idea. However, despite all its undeniable mathematical elegance and sophistication, string theory does face some persistent, significant limitations. Things our source material really digs into.
Okay, what are the big ones?
Well, one major point of contention is this issue of static compactification, the idea that these extra dimensions are just fixed, curled up in a specific way. But the theory doesn't really provide a dynamic origin or a natural explanation for why they're compactified like that or why that specific shape.
So it's just assumed.
It's essentially an assumption, yeah. A feature you have to build into the theory rather than something the theory naturally predicts or explains. It leaves you wondering, well, why this structure? Why not another?
Okay, what else?
Another big one is its trouble explaining the precise values of fundamental physical constants. You know, the speed of light, Planck's constant, the electron's mass, these numbers that define our universe's laws.
They seem pretty arbitrary, right? Why those specific values?
Exactly. String theory often requires what's called a landscape of possible universes. It suggests there might be a huge number, maybe 10 to the 500, or even more of different ways those extra dimensions could be curled up, each leading to a universe with different constants.
Whoa, that's a lot of universes.
It is, and it kind of implies this fine-tuning problem. Our universe just happens to have the right values for life, maybe because we live in one of the few habitable ones out of a vast multiverse, but it doesn't give an inherent mechanism for why these constants emerge with the values they have from the theory itself. It feels a bit like saying, we're here because we're here, without that deeper causal explanation.
Right. It feels a bit like kicking the can down the road.
Some critics would say so, yeah. And perhaps the most critical limitation, the one you hear most often, is the lack of directly testable predictions.
Ah, the testability issue.
Right. Its abstract nature means many of its unique predictions, like the existence of the strings themselves or specific supersymmetric particles, often occur at incredibly high energy scales, far beyond anything we can currently reach with particle accelerators or even foresee reaching anytime soon.
So we can't really prove it right or wrong experimentally.
Direct proof is extremely difficult, yes. Which leads to the question, if you can't test it, is it truly science in the traditional falsifiable sense? That's a big debate.
Yeah, that's a tough one.
So what's really fascinating here, and kind of a powerful insight, is how string theory, despite being so mathematically beautiful, leaves these crucial gaps. It's like having this incredibly detailed, gorgeous map.
But you don't know how the mountains formed or why the rivers flow where they do.
Exactly. You don't know how the terrain formed, why the features are what they are. And this is precisely where our new framework, the HHHHCR TOE, steps in. It's trying to address these fundamental limitations head-on by proposing a really different kind of universe.
So the stage is set. We have string theory, elegant, mathematically sophisticated, but maybe a bit rigid, relying on these static, curled-up dimensions and inert brains. Now, here's where it gets really interesting. Our source introduces something called Hyperspace Physics, and specifically the HHHCR TOE, the hyperfractal, hypersymmetry, hypergravity, coherence, resonance theory of everything.
Quite a mouthful.
As a direct, comprehensive response to exactly these limitations we just discussed.
Please.
What's the fundamental shift in thinking this new theory brings? It sounds like it's challenging some very basic assumptions.
It truly is. The HHHCR represents a really profound departure from conventional physics, especially string theory. It proposes a universe that is fundamentally dynamic, active, and emergent rather than, passively pre-structured.
Dynamic, active, emergent.
The core departure is this. Instead of fixed pre-structured dimensions just being there, hyperspace physics posits a self-organizing, recursive, and coherence-driven emergence of dimensional structure.
Coherence-driven, what does that mean?
It means dimensions aren't just the background stage. They actively unfold, evolve, and organize themselves based on an underlying principle of coherence or resonance. Imagine the universe not as a static blueprint, but as a constantly growing, unfolding, self-designing entity.
Okay, that's a very different picture.
It is. And this dynamic view brings us to the core concept of hyperfractal layers. These are presented in stark contrast to string theory's passive branes.
Right, the static sheets.
Exactly. While branes are described as static, smooth surfaces, hyperfractal layers are anything but inert. Think of branes as that flat sheet of paper, the fixed stage. Hyperfractal layers, on the other hand, imagine living, evolving fractal structures.
Like a Mandelbrot set, but in higher dimensions and alive.
Kind of. Think of the intricate, self-similar branching of a tree or the recursive patterns in a coastline, but existing in higher dimensions. They're not curled up and hidden away statically. They are active participants, dynamically unfolding through continuous interaction.
Unfolding how?
Through fundamental coherence fields, specific resonance thresholds, and a unique force called hypergravity coupling. This dynamism lets them influence physical phenomena in real time. They exhibit fractal self-similarity and adaptive scaling.
Adaptive scaling.
Meaning they can adjust their properties, their very structure, to suit different physical regimes from the quantum scale all the way up to the cosmic. They aren't fixed, they adapt. So they're like the actors, the architects, and the evolving stage all rolled into one.
Wow. Okay, that's a lot to take in. So what are the key building blocks here? You mentioned coherence fields.
Right. To really grasp the HHHCR TOE, we need to look at its key concepts. First, these coherence fields. This is proposed as a truly fundamental field, like an underlying fabric, or maybe the ontological generator of reality itself.
The generator.
Yeah. It's not just another force like electromagnetism. It's conceived as the master conductor that governs everything, how particles resonate and align, the precise emergence of physical constants, the fundamental forces we see, the overall structure of the universe across all scales. It's the source from which existence, in its most fundamental form, arises. Think of it as the universe's inherent ability to self-organize and literally resonate into being.
So coherence isn't just a property, it's the source.
That's the idea. Then we have hypergravity coupling. Now, this isn't just taking Einstein's general relativity gravity as space-time curvature and extending it. It's proposed as a distinct coherence-based coupling force.
How is it different?
It emerges directly from the dynamic interactions between these hyperfractal layers and the coherence fields. It's a novel type of gravitational interaction arising from this interplay within the theory's foundation. It suggests gravity has a far more intricate, active role than we currently understand. Almost like gravity isn't just about mass pulling on space-time, but about how these layers resonate with each other through coherence.
Interesting. A new kind of gravity.
Potentially, yes. And perhaps one of the most radical ideas is multi-vector temporal dynamics.
Okay, break that down for me. Sounds intense.
It profoundly challenges our usual linear understanding of time. Instead of time being just a single arrow pointing from past to future.
Like a river flowing in one direction.
Exactly. This theory considers time as a multidimensional vector. It has various interacting components or axes. The source mentions things like coherence time, resonance time, quantum time.
Multiple kinds of time.
Essentially, yes.
Yeah.
Instead of one river, imagine a complex delta with many interconnected streams, each representing a different aspect of time's flow or function. This suggests a far more complex, layered, active, temporal reality than we usually think about, where different aspects of time can influence each other and contribute to how the universe unfolds.
Okay, my brain is officially bent. Multiple time dimensions.
It's definitely a paradigm shift. But the grand ambition of this whole framework is to offer potential solutions to some of physics' deepest, most persistent problems.
Like the constants problem.
Exactly. The origin of physical constants isn't explained by fine-tuning or this vast landscape anymore. Instead, they emerge inherently from specific coherence relationships within the hyperfractal layers. They're not arbitrary. They're intrinsic to the universe's self-organization.
So the universe tunes itself.
In a way, yes, through resonance. Similarly, the emergence of dimensions isn't just assumed. They dynamically unfold from this coherence-driven process adapting to conditions. And fascinatingly, consciousness itself is reframed.
How so?
It's not seen as just a byproduct of complex matter like brain activity. It's proposed as a fundamental resonance phenomenon, intrinsically linked to the universal coherence field, almost a fundamental property of reality itself.
Wow.
So if we connect this to the bigger picture, the HHHCR isn't just tweaking existing physics. It's presented as a superseding generalization. It offers this coherence-based, fractalized, resonance-resolved framework where dimensions, forces, constants, even consciousness arise through self-organization. It's not relying on preset symmetries or static geometries. It's a truly bottom-up, emergent, deeply interconnected view of the cosmos. Everything is constantly being built in tune from this fundamental field of coherence.
This is where the rubber meets the road, then, or maybe where the brains meet the hyperfractal layers. Because while both theories clearly use multidimensional constructs, their nature sounds profoundly different, as you've laid out. What are the key similarities, just so we're clear? And then more importantly, what are the critical defining differences in how they view these fundamental structures?
You're absolutely right. At a surface level, there are some conceptual similarities that could perhaps be a bit misleading if you're new to this. Both string theory and the HHHCR definitely agree on the need for a multidimensional foundation. They both operate in realities beyond our usual 4 dimensions. String theory's brains are smooth surfaces in a higher dimensional bulk. Hyperfractal layers span these recursive hyperdimensional scaling structures. So both acknowledge reality is bigger, more complex than what we directly see.
More than meets the eye.
Exactly. Furthermore, both theories see these constructs as a kind of scaffold for physical emergence. In string theory, brains are where string interactions happen, leading to particles and forces. They're the stage.
Right.
Similarly, in HHHCR hyperfractal layers are these coherence-rich scaffolds where constants, forces, structures emerge through interlayer resonance. So both provide a framework for the physical universe to manifest, just through very different mechanisms.
Okay, both provide a stage, just different kinds of stages.
Yeah. Kind of, yeah. And finally, both are seen as embedded within higher frameworks. Brains sit in the string theory bulk. Hyperfractal layers are within this coherent, structured hyperfractal manifold, this intricate, recursive architecture. So neither proposes a simple, isolated universe.
Got it. So multidimensional, providing a basis for physics and part of a bigger structure.
Right.
But now the differences.
Right, and this is where our deep dive really shows the contrast. Let's start with structural complexity. String theory's brains, typically modeled as smooth, continuous, differentiable surfaces. Think perfect, flat, or smoothly curving cosmic sheets.
Like ideal mathematical objects.
Pretty much. Hyperfractal layers, in stark contrast, exhibit fractal recursion, self-similarity, and scale-dependent structural patterns. They are not smooth. They're intricately structured, with repeating patterns at different scales, like that fern frond or snowflake analogy.
Infinitely detailed.
Exactly. And this inherent fractal nature supports nonlinear transitions and what are called quantized coherence plateaus. These are like stable points of resonant energy, allowing for complex emergent behaviors across different scales. So it's the difference between a pristine, smooth surface and an infinitely detailed, self-replicating, almost living one.
So it's not just a difference in shape, but in how they're fundamentally built. And how that structure lets them behave.
Exactly. That leads directly to their very different dynamism and scaling behavior. Brains in string theory. They're defined within fixed topologies, fixed dimensions. Their compactification is static, assumed from the outside. They are fundamentally unchanging. They don't grow or adapt.
Set in stone, basically.
Right. Hyperfractal layers, on the other hand, arise dynamically through this coherence-driven recursive layering process. They feature adaptive scaling, both continuous and plateau-based, meaning they can fluidly transition between different physical regimes, adapting to conditions within the universe. It's like a self-tuning instrument adjusting its own strings based on the music, rather than a fixed, pre-tuned one.
Okay, much more flexible.
Much more. Their mechanism of interaction is another key differentiator. Brains interact mostly through geometric deformation or boundary interactions where strings attach or fields meet at the edge. It's a relatively static geometric relationship.
Right.
Hyperfractal layers, however, interact dynamically via resonance thresholds, coherence gradients, and hypergravity coupling. This forms a complex feedback-driven system. Forces and constants aren't static. They modulate in response to the specific coherence conditions present. It's a much more active, responsive, interconnected way of interacting, like a vast cosmic network constantly sending signals and adjusting its connections based on resonance.
That sounds way more interactive.
It is. And their role in dimensional emergence is maybe the most profound distinction. In string theory, brains exist within predefined dimensions. The dimensions are just assumed, part of the setup. They're containers. But for hyperfractal layers, they actually generate dimensions dynamically. Each layer is said to encode potential dimensionality through its coherence depth and fractal scaling functions. Dimensions aren't just there, they are actively brought into being through this recursive unfolding, like a flower blooming, revealing new layers as it opens.
Whoa. Okay, so dimensions aren't fundamental, they're emergent properties of these layers.
That's the core idea, yes. Then, the relation to physical constants. String theory suggests constants come from string vibration modes and brain geometries, often needing that tuning or landscape selection to match what we see, like picking the right universe from the menu.
The fine-tuning problem again.
Right. HHHCR-TOE offers a more intrinsic explanation. Constants emerge directly from the interlayer coherence relationships, with resonance determining their exact values. This implies a mechanism for real-time tuning or variation based on cosmic conditions, not just a static value. Imagine a universe where the speed of light isn't absolutely fixed, but is fine-tuned by the resonant harmony of its underlying structure.
That's a radical idea, constants changing.
Potentially subtly varying, yes, based on coherence. Finally, their ontological status, what they are. Brains are passive geometrical surfaces just hosting interactions. The stage.
Got it.
Hyperfractal layers, conversely, are active recursive participants in cosmic self-organization. They can align, modulate, cohere physical phenomena across all scales. They're integral to the universe's ongoing creation. They are both the stage and the constantly evolving actors, shaping reality from within.
So what does this all mean for our understanding of reality? It sounds like we're moving from a universe with a static backdrop to something much more alive, adaptive, and maybe even self-aware in a way.
It definitely raises that crucial question, what are the conceptual implications of this really profound shift? Firstly, it's a major move from a static to a dynamic ontology. In string theory, reality is often built on a fixed background, set laws. HHCR-TOE redefines the very nature of dimensional structure as fluid, emergent, recursively generative. Reality isn't just there, it's constantly being made and remade through coherence.
Actively participating.
Exactly. Secondly, it proposes a unified emergence versus what might seem like more disjoint mechanisms in string theory. String theory uses strings, brains, compactification, supersymmetry, somewhat separate pieces. Hyperspace physics suggests a more unified path. Space, time, mass, forces, even consciousness, all emerging from one underlying principle. Coherence dynamics, one elegant source.
Simpler in principle, maybe.
Eventually more unified, yes. And perhaps most poetically, it shifts our view from passive geometry to what the theory calls living geometry. Hyperfractal layers suggest the universe's architecture isn't inert. It's alive with resonance, continuously adjusting, adapting, self-modulating. This introduces the profound idea of inherent intelligence and adaptability woven into the very foundation of physics, a universe actively participating in its own unfolding, almost like it's thinking or feeling its way into existence.
Okay, living geometry. That's a powerful phrase. Every great theory has its language. And in physics, that language is mathematics. If the conceptual differences are this profound, I imagine the mathematical underpinnings must be equally, radically different. How do these two theories fundamentally differ in their math? My brain is definitely getting a workout trying to visualize these hyperfractal layers.
Absolutely. The mathematical frameworks really do mirror these deep philosophical and structural splits. String theory, with its smooth brains, is firmly rooted in classical geometric frameworks. Think Riemannian geometry, Minkowski geometry, standard stuff for physicists.
Right, curvature, space-time, etc.
Exactly. Brains are described as smooth, differentiable surfaces in fixed dimensions. It uses well-established tools, differential geometry, tensor calculus. Geometry here is essentially a passive background, a static stage for strings and brains. It's beautiful math, elegant, but describes a fixed setup.
Okay. Standard toolkit.
Right. Hyperspace physics, though, it ventures into something called Noetherian-Finsler geometry. This introduces direction-dependent metrics.
Direction-dependent metrics. What does that even mean?
Okay, imagine the fabric of space itself doesn't just bend like in Einstein's theory, but its properties subtly change depending on the direction you're moving or looking, almost like walking on a surface where friction is different depending on whether you step north or east.
Whoa, okay.
This direction-dependent metric allows for a much more dynamic, responsive universe. And crucially, this framework also integrates fractal and hyperfractal metrics to capture that layered emergence and the coherence plateaus we talked about.
So it needs new kinds of math.
Yes. It embraces non-differentiable structures, places where things aren't smooth, like the edges of a fractal. This requires more generalized tools, like fractional calculus, to describe these recursive, non-smooth regions. And critically, in HHHCR-TOE, space and time aren't just assumed, they emerge dynamically from resonance fields. The geometry is active, alive.
Wow, that sounds incredibly complex. So the math itself isn't just describing reality. It's almost part of reality's dynamic unfolding.
That's a great way to put it. It's like an internal language of emergence. Regarding dimensional structure and dynamics, string theory works in a fixed number of dimensions, usually 10 or 11. Extra-wise static, compactified, hidden, no internal mechanism for dimensions to arise there assumed.
Just part of the setup.
Right. HHHCR2E, though, proposes dimensions unfold via coherence reduction cascades through the hyperfractal layers. Each layer is a recursive step in dimensional emergence, featuring both discrete plateaus and continuous scaling. It uses this concept of multi-vector space and time, multiple temporal axes, primary time, resonance time, coherence time, and vectorized spatial curvature. Dimensions are fluid, nested, adaptive, like layers of an onion peeling back or a complex organism developing.
Multiple time axes again. Okay.
It's fundamental to the theory. Their algebraic structures and symmetries also differ hugely. String theory relies heavily on standard tools like Lie algebras, superalgebras, group theory for its symmetries, gauge symmetries, supersymmetry. These dictate how particles interact, transform. Symmetries are often broken by boundary conditions or compactification. The algebra governs string vibrations.
Okay.
Hyperspace physics employs hypersymmetric algebras. These extend beyond standard groups. They include dynamic symmetry breaking, resonance operators, coherence field symmetries. It incorporates higher-order systems like octonions, Clifford algebras. Symmetries here aren't fixed. They're coherence-dependent, adapting dynamically. Resonance itself acts as an operator for selecting or emerging symmetries. Symmetries are actively chosen or formed by the universe's coherence.
So symmetries aren't fundamental laws, they're outcomes.
Outcomes of coherence and resonance, yes. When it comes to field equations and force dynamics, string theory uses Lagrangians, these energy descriptions, over smooth manifolds. Gravity comes from Einstein-like equations in higher dimensions. Brane interactions are boundary effects.
Standard approach.
HHHCR-TOE integrates coherence fields, hypergravity couplings, resonance thresholds into extended Lagrangians. Coherence dynamics are embedded into energy conservation laws via Noetherian symmetries of coherence. Force dynamics aren't just geometric, they're resonant, emerging from fractal scalar feedback loops across layers. The equations themselves have nonlinear stochastic fractal terms to capture this real-time complex evolution. It's like the equations are alive and adapting.
The equations themselves are adaptive.
That's the implication. Finally, the temporal structure and emergence. String theory. Time is a single linear parameter in a smooth manifold. Interactions happen on a predefined timeline, a fixed clock.
Simple time.
Relatively, yes. HHHCR-TOE models time as that multivector structure, distinct interacting axes: coherence time, resonance time, entropic time, quantum time. Temporal emergence itself is a key dynamic, generated by coherence decay and resonance amplification. Time is an active participant, not just a passive background. It's not just where something happens, but when and how across multiple interconnected temporal flows.
This mathematical divergence really highlights a deeper philosophical split, doesn't it?
Huh.
It sounds like the HHHCR-TOE is painting a picture of a universe that's constantly creating itself moment by moment using this incredibly complex adaptive math.
Indeed. It's a shift from static modeling of a predefined universe to this recursive, coherence-driven emergence. Structure, force, time, dimension, all dynamically actualized, constantly brought into being through resonance.
Okay, but the best theories, of course, are the ones we can actually test. String theory has often been criticized, quite heavily actually, for making predictions at energy scales we just can't reach, billions of times higher than anything on Earth. What's the promise of hyperspace physics here, in terms of real-world testable predictions, maybe even new technologies? This is where it gets tangible for me.
And this is a critical area where hyperspace physics really aims to distinguish itself significantly. The HHHCR TOE is focused on testable resonance phenomena and potential coherence-based engineering. Unlike string theory, which, as you said, is largely confined to those inaccessible energy scales, often remaining abstract, this theory actively seeks concrete ways for empirical verification, often at energy scales potentially within reach.
Okay, so how could we test it?
Let's dig into some of the potential coherence-based experimental predictions. In high-energy physics, HHHCR TOE predicts these coherence thresholds in particle interactions,
Coherence thresholds.
meaning under specific conditions, extreme resonance, specific energy inputs, fundamental constants or force couplings, the strengths of forces, might subtly shift or deviate from known values. Imagine hitting a specific resonant frequency that slightly changes the rules of particle physics.
Wow, like tuning a radio and suddenly gravity gets weaker.
Maybe not that dramatic initially, but potentially measurable deviations, yes. Experiments at places like the LHC or future colliders could look for these non-linear deviations from the standard model, especially under carefully controlled, resonance-rich conditions. We might see particles behaving unexpectedly, decaying differently when these coherence thresholds are crossed.
Okay, looking for anomalies under specific conditions.
Exactly. We might also see signatures of hypergravity coupling. This could show up as deviations in mass energy behavior or unusual force mediation at specific threshold energies. For example, if you achieve a certain coherence level, maybe you observe a tiny temporary change in an object's inertia or an unexpected force not explained by the known fore. These would be direct clues pointing to interactions across hyperfractal layers. Tangible evidence.
Evidence of those layers actually doing something.
Right. Furthermore, the theory suggests possibilities for gravitational modulation. Under extreme coherence, maybe in ultra-cold quantum states like Bose-Einstein, condensate's gravity itself might shift observably. This could reveal variable gravitational constants or anisotropic field signatures, gravity not being uniformly the same everywhere or always.
Variable G, that's huge. That contradicts standard physics.
It's a direct contrast to string theory's rigid constants, yes, a revolutionary discovery if observed. HHHCR TOE even predicts potential for tiny, maybe oscillatory variations in other constants, like the fine structure constant governing electromagnetism. These variations might correlate with resonance field fluctuations, maybe even solar cycles, or large-scale cosmic coherence shifts. Another clear empirical distinction, a path for testing.
So we're not just talking about tiny theoretical shifts, but potentially entirely new observable phenomena and variations in constants. That would completely upend physics, wouldn't it?
Monumental shift, yes. Fundamentally redefining. But the implications go beyond just observation. They suggest entirely new coherence-driven technologies. This is where it gets incredibly exciting for applications.
Okay, tell me more. Like what?
One thrilling area is resonance energy systems. The theory posits that coherence tuning, carefully aligning vibrational frequencies, could allow energy extraction or modulation from structured vacuum fields. This connects to ideas sometimes called zero-point energy, but framed very differently here. Governed by something called the vacuum coherence tensor, describing energy potential in coherent space. Imagine clean energy not from burning fuel, but by tapping into the universe's inherent resonance.
Wow. Free energy from the vacuum. Sounds almost sci-fi.
It's a bold prediction, but grounded in the theory's framework. Then there's coheraputers. Imagine a new class of computation based not on bits or even qubits, but on precisely tuned resonance field states, manipulating information through harmonious alignment of coherence fields.
Computing with resonance.
Exactly. Such coheraputers could potentially outperform even quantum computers in adaptability, stability, coherence, retention, opening new frontiers in AI, complex problem solving, maybe tackling problems currently impossible for any computer.
Okay, that's mind-blowing. What else?
The theory also points towards space-time engineering. Technologies like inertial dampening, making objects resist changes in motion for smooth, rapid acceleration.
Like inertial dampers in Star Trek?
Kind of, yeah. Or resonant propulsion, moving through space by manipulating its coherence, not brute force thrust. Even localized temporal modulations subtly altering time flow in a small area. This is different from brute force space-time warping like Alcubierre drives, which need maybe impossible energy. It's about aligning with the universe's dynamics, using coherence gradients.
Gentle manipulation, not brute force.
That's the idea, and maybe most intriguingly, biocoherence interfaces. It suggests biological systems, cells, brains are fundamentally natural coherence engines operating via bioelectromagnetic fields and resonance.
Life as a coherence phenomena.
Essentially. This could lead to revolutionary medicine-targeted healing by restoring cellular coherence, neuromodulation by influencing brain states with resonance, even synthetic intelligence interfacing directly with biological coherence. It bridges physics and life itself in a way string theory generally doesn't.
Physics meets biology meets consciousness.
It points that way. Now, this raises an important question. How would we actually detect these coherence fields? They're fundamental. The theory points to indirect observables. Maybe anomalous phase shifts in highly coherent laser systems, subtle density fluctuations in ultra-cold condensates, deviations from inertial symmetry in rotating superconductors, maybe long-range entanglement persisting longer than expected, hinting at an underlying stabilizing coherence. These are all potentially testable signatures.
It's incredible to think these ideas aren't just blackboard exercises, but could lead to new energy, propulsion, even medicine. It brings the abstract right into the tangible. Which is what you want from a theory of everything. But I can just hear a traditional physicist saying, that sounds speculative, too good to be true. What's the biggest hurdle to making coherent or space-time engineering real?
That's a crucial and very fair question. The biggest obstacle right now, it's the precise, controlled manipulation of coherence fields at the necessary scale. We're talking about mastering the very subtle, foundational frequencies and resonance patterns that, according to this theory, build reality.
That's hard.
Extremely. While the theory outlines how these things emerge, building a device that can reliably tune or amplify coherence fields to the required intensity for, say, resonant propulsion, that's an enormous engineering challenge. It's like having a perfect musical score, but not yet having the instruments or the conductor skilled enough to play it. But the theoretical roadmap is there. And those initial experimental signatures we discussed, they're precisely what could give us the first practical handles. The first steps towards measurement and then influence. It's about developing the tools to first measure, then interact with these subtle underlying patterns.
Got it. Huge challenge, but a path exists. Now, beyond the equations, beyond the experiments, there's always the deeper why, the philosophical implications.
Yeah.
It seems HHHCR radically redefines the very ontology of the universe, our fundamental idea of what exists now. What does it mean for reality, consciousness, maybe even the universe's purpose?
This is where hyperspace physics truly steps beyond just physics and into the nature of existence itself. Let's compare the foundation of reality, passive versus active. In string theory, the ontology is largely reductionist. Brains are passive scaffolds. Dimensions are fixed, chosen to fit data, not evolving. No inherent agency or feedback in the dimensional structure itself. Emergence is a consequence of fixed laws.
The stage is set, the actors follow the script.
A good way to put it. In stark contrast, hyperspace physics posits hyperfractal layers as active generative structures. Dimensional expressions of a universal resonance field, actively modulating, aligning, generating coherence. They participate in self-organization. This implies reality is recursive, self-similar, suggesting a holofractal metaphysics, the whole in every part, the part reflecting the whole, like a hologram. Deep interconnectedness, reality constantly referencing and recreating itself.
Okay.
This deep ontological difference extends to the emergence of time, space, and consciousness. In string theory, time and space are background parameters, containers existing before physics happens. Consciousness, not really addressed, usually outside physics. Emergence is mechanistic, derived from things like compactification.
Separate pieces.
Right. In hyperspace physics, time is multivectorial, layered, coherence decay, quantum intervals, cosmic cycles. Space isn't inert. It arises from recursive unfolding of dimensional coherence, adapting. And profoundly, consciousness is reframed as a resonance with the universal coherence field. Not a byproduct of matter, but a structural function of reality's fundamental dynamics. The theory explicitly says, coherence is not a symptom of order. It is the generator of form, force, and sentience.
Sentience generated by coherence. Wow. So are we saying the universe itself is intelligent? That's a huge leap for many people from traditional physics. It sounds almost spiritual.
That's a natural reaction, and it's important to clarify. HHHCR isn't proposing, a conscious entity sitting out there. It's suggesting a self-organizing cosmos and resonant intelligence that's embedded within the fabric of reality itself.
Intelligence in the structure.
Yes. The universe isn't just governed by fixed laws, but is inherently self-selective, self-tuning. The existence of coherence plateaus, adaptive force thresholds, resonance-modulated constants, these imply an active intelligence, a capacity for self-regulation and optimization built into reality's architecture, like viewing the universe as a meta-organism or as intelligent structure, constantly evolving by maintaining and optimizing coherence across all scales.
This intelligent structure.
It contrasts sharply with the anthropic fine-tuning of string theory's landscape, where our universe is just a lucky draw. Here, fine-tuning isn't accidental. It arises from resonant feedback and coherence stabilization, an inherent drive towards optimized patterns.
Purpose emerging from the physics itself.
You could interpret it that way. This leads to the role of self-similarity and ontological recursion. Hyperfractal layers obey recursive nesting. Higher dimensions contain scaled echoes of lower ones, and vice versa. Self-reflection. This allows for holographic coherence, information redistributed fractally across scales. The implications for meaning, perception, cognition are profound. Reality perceives itself through coherent patterns manifesting as awareness, agency, evolution. Our consciousness isn't separate, it's a localized manifestation of this universal coherence and self-perception.
Mind blown.
Again, it's deep stuff. Finally, this leads towards a coherence-centered cosmophilosophy, where traditional physics often puts math first. HHHCR suggests coherence precedes math. Math becomes a resonance language arising from the ontological structure, not imposed on it. It fundamentally shifts from a universe of fixed laws to a universe of living patterns, resonant, recursive, self-realizing. A framework integrating physics, consciousness, complexity into one dynamic ontological field. Reality as a process, not just a static thing.
It sounds like we're talking about a paradigm shift, not just in physics, but in how we conceive of existence itself. It truly is a living geometry, constantly actualizing its own potential.
That's precisely the point. An active, dynamic universe, realizing itself through resonance and coherence, suggesting inherent self-organization, maybe even self-awareness in a very fundamental sense.
Okay, but any new, groundbreaking theory, especially one that's ambitious, challenging, and established giant like string theory, is bound to face scrutiny. Objections. Our source anticipates this, directly addressing potential critiques from the string theory perspective. Let's unpack some of those. How does HHCR respond? I'm particularly curious about how it handles the mathematical rigor critique.
Indeed, a challenger theory needs robust defenses. Let's tackle critique 1, lack of mathematical formalism, the objection. String theory has this highly developed, rigorous math, Riemannian geometry, Lie algebras, supersymmetry. HHHCR being newer might seem more conceptual, less formalized.
Right, less equations, more ideas.
That's the perception. The response from hyperspace physics is it introduces new mathematical tools precisely because the old ones aren't adequate for a dynamic, fractal, coherence-driven universe. Tools like Finsler geometry, fractal calculus, hypercomplex algebra, coherence resonance operators. These are not less rigorous, the argument goes, but operate in non-traditional mathematical domains suited for recursive, coherence-based systems. The theory is actively being translated into extended Lagrangians, multi-vector field equations, algebraic resonance structures. The claim is the math is ontogenetic emerging from coherence rather than presupposed. A new language for a new reality.
Okay, so the math is different, not necessarily weaker.
That's the defense. Next, critique 2, no direct experimental validation. The objection. Like string theory, HHHCR lacks direct confirmation. Coherence fields, hypergravity not yet measured.
The testability issue again from the other side.
Exactly. However, hyperspace physics counters by predicting specific, testable signatures at accessible energy scales and in lab settings, unlike many string theory predictions. Those fluctuations in constants under resonance, anomalous couplings, time asymmetries, condensed matter effects. The key distinction claimed is testability with current or foreseeable tech, not just far future possibilities.
That's a powerful counterargument. It's not trust us, it's here's what to look for with tools we have or can build.
Precisely. Then we face critique 3, overly novel terminology. Critics might say hyperfractal, multivector time, sound speculative, lack clear analogs, make it hard to engage.
Jargon obscures rather than clarifies.
That's the worry, the response. Novel paradigms require novel language, just like quark or brain once sounded weird. These new terms are supposedly precisely defined, encoding formal distinctions essential to the framework's mathematical and experimental depth. Necessary terms, not just rhetoric.
Okay, new concepts need new words. Fair enough.
Then there's critique 4. No integration with supersymmetry or the standard model. The objection. It doesn't seem to fit with well-tested physics like the standard model.
It ignores what we already know works.
The theory responds by clarifying. It doesn't discard the standard model. It extends and recontextualizes it. Particle families, masses, forces are modeled as outcomes of coherence modulation across layers, a deeper explanation. Supersymmetry, key in string theory, is generalized into hypersymmetry, including coherence-based phase transitions, explaining mass hierarchy via resonant alignment, offering deeper explanations than the standard model's empirical parameters.
So it builds upon rather than replaces.
That's the claim. A common philosophical critique is critique 5. The framework is metaphysical or philosophical. Terms like living geometry, coherent intelligence sound like metaphysics, not rigorous physics.
Too philosophical, not enough science.
Right, the response. The boundary between metaphysics and physics shifts with discovery. Living geometry just means geometry evolving via recursive feedback and coherence. A testable, formalized proposal, not mysticism. It's a paradigm shift, where structure and coherence are primary, empirically discoverable, not just abstract concepts, putting the meta onto a physical footing.
Redefining the boundary. Interesting.
Regarding critique 6, lack of predictive power, objection. Without concrete numbers, it might be unfalsifiable, too broad. HHHCR-TOE asserts it does predict. Existence of coherence plateaus for particle families, variable constants under coherence fluctuations, multi-vector temporal phase signatures and entanglement decay, measurable, mass shifts near hypergravity coherence collapse. These are being modeled for simulations and experiments, offering specific points of falsification.
So there are numbers to test, eventually.
Yeah, that's the goal. Finally, critique 7. Novelty equals speculation. Argument. Unfamiliar structures must be speculative, less credible just because they're new. The response emphasizes, novelty is a requirement for scientific evolution, not a weakness. Just as general relativity reframes spacetime, HHHCR-TOE reframes dimensionality and force via coherence layering. It's presented as an ontological refoundation with clear internal logic, not mere speculation, pushing frontiers.
It's clear this theory isn't shying away from the hard questions or the skepticism. It really pushes us to rethink fundamental assumptions, suggesting novelty here could be a sign of progress, not a flaw.
If we pull back and look at the bigger picture, this comparison between string theory and HHHCR-TOE really shows a critical inflection point, maybe in fundamental physics. String theory, for all its elegance, can seem constrained by static assumptions, predefined dimensions, passive branes, fixed constants. HHHCR-TOE challenges all that, proposing a universe that's fundamentally dynamic, active, alive in its very geometry.
That's right. What really hits me from this deep dive is how profoundly this new theory challenges our ingrained assumptions. It's a fundamental shift from a universe of passive geometry hosting things to active coherence generating things.
Exactly.
From fixed assumed spacetime to layered dynamic temporal systems. From constants that just are and seem weirdly fine-tuned to resonance-tuned emergence. From maybe metaphysical dualism to ontological recursion, where everything is deeply interconnected and self-generating.
You've captured the essence of the shift. At its heart, this theory introduces a profound principle. Coherence is the seat of structure. Resonance is the law of emergence. Reality is recursive intelligence. The universe isn't a closed mechanical system on static rules, but an open coherence engine, sustaining itself by cascading order through fractal resonance, hyperdimensional recursion, intelligent pattern generation. Dimensions are alive, time is layered, constants tunable, intelligence emerges from structure.
And what does this mean for the future, for us? It lays groundwork for incredible possibilities, doesn't it? Experimental breakthroughs in coherence-driven energy, field manipulation, computing.
The potential is vast, if the theory holds.
New physics of mass, force, time, based on this dynamic coherence. A redefinition of cosmology, not just expansion, but unfolding of coherence into form. And maybe most profoundly, that bridge between physics, biology, even consciousness. A unified framework revealing the resonant unity of everything.
Ultimately, hyperfractal layers don't just replace brains conceptually. They aim to reveal a deeper truth. Reality isn't built from strings vibrating in voids, but from resonant layers of coherence harmonizing into being. It tries to transcend and absorb useful elements of older theories, integrating them into this broader coherence ontology, suggesting a more active, self-organizing universe than we've maybe dared to imagine before.
This really feels like the birth of a new science. Not one solely of control, maybe, but of alignment. Not just measurement, but meaning. A science where the observer, the observed, the act of coherence itself form this triadic whole. Co-authors of an emergent universe. Wow. We certainly had a deep dive today. My mind is absolutely reeling. What stands out most to you after exploring these truly mind-bending concepts?
For me, it's the shift from seeing the universe as a set of rules being followed to seeing it as a system actively finding its way, learning, adapting through resonance. That idea of living geometry really resonates, pun intended.
Yeah, me too. That's all for this deep dive. Thank you so much for joining us on this journey to the absolute cutting edge of physics. Until next time, keep exploring, keep questioning, and keep diving deep.